Okay, another way to prove non-regularity is by closure properties. So as a concrete example, consider two languages. H is all the binary string with equal number of zeros and one, which we already, by the way, saw in one of the exercises that it's not regular. And the other one is our old friend H prime, which is all the string 0 to the k1 of the k, which we already seen several times, which is not regular. And the claim is that now it's straightforward. Once we know that H prime is not regular, showing that H is not regular, it's very easy. And the reason is because what is H? H is just, or if you want H prime. H prime, right? This is the, H prime is a subset of H, right? H prime is all the languages where we have zeros, k zeros, and k1. All the zeros follow all the ones. H, on the other hand, is all the string with equal number of zeros and one. So if we take H and we intersect it with the language 0 to the star, 1 to the star, right? Let's call it language of zeros to the star, 1 to the star, right? Then we get H prime, right? Now, what do we know? We know that H prime is not regular. On the other hand, we know that 0 star, 1 star, this is of course a regular language. Well, to begin with, I just gave you the regular expression, right? And also it's very easy to build a DFA for it, right? It's just start state, gets zeros as much as you want, then take a 1, go to the state, and then get 1, and stay with 1. And if you get 0 here, okay. So in fact, here is a DFA for it, right? So this is a DFA, this is a hell state, right? So this is a DFA for this language. We have a regular expression, we have a DFA, and you can also draw an NFA. So this is easy. Okay, so this language is regular. H prime is not regular. Now what happened if H is regular? Let's assume for a second that H is regular. Okay, so we take a regular language and we take another regular language and we take their intersection. Well, intersection of regular languages is a regular language. We proved that. This was the product construction of automatas, right? So if H was regular, then the intersection of H, this intersection would also be regular, which is a contradiction to the fact that H prime is not regular. So we got a contradiction, okay? So that's the proof. Here's the proof in words. In general, the strategy works as follows, right? We take a bunch of regular languages that we know that are regular. We take this unknown language that we want to prove it's not regular. We apply a sequence of closure properties, intersection, difference, prefix, suffix, whatever. And we get some output language which we know is not regular. Right? And then the only way for this to happen, since this is closure properties that are closed for regular languages, the only way it can happen is if this unknown language is in fact not regular. So that's the proof strategy. And the nice thing about this proof strategy is that if you can apply it, it's much easier than the previous strategy of fooling set, which requires, in fact, understanding the language in a much more low-level understanding. Okay. So what are the techniques that we have for proving non-regularity? We have this proof of, proving that there are a lot of distinguished prefixes, namely that proving that there is big sets or big fooling sets, unbounded fooling set, which implies the language is irregular. We had the technique of closure property, starting with a bunch of regular languages, applied them to the new language, and get a non-regular language, and as such conclude that the original language was not regular. And the third technique, which we did not speak about at all, although in fact I hinted about it in the beginning, is the pumping lemma. So let me recall quickly what the pumping lemma is, because I kind of want you to know about this argument, because it makes another way of thinking about what's going on. So the basic idea of bound regular languages is that if we have a language and we think it's regular, we assume that it's regular, then it has a finite DFA. And then the idea is that if you apply a long enough, if the language has arbitrarily long strings, then when you apply an arbitrarily long string to the automata, there must be a string where it has a loop, right? Because the number of states in the automata is finite, so there must be a string in the language which is longer. As such, when you apply to the language, you get a path in the automata to the accepting state of the string, which has a loop. And the idea is that once you have a loop, this loop part, right, you arrive to a state, you go around, and then you go to the state again. This loop, you can repeat it as many times as you want, right? If you can repeat it as many times as you want, you get a new string which must also be in the language. And then you argue that this is not possible, that your language cannot have this repetition repeated, which implies that indeed it cannot be regular. So this is the pumping lemma argument. It's somehow more painful to understand than the fooling set. The fooling sets are somehow more intuitive, but inherently the argument is equivalent. So those are the three techniques that we are going to use to prove non-regularity. That's it for now.